Hey everybody, how has your first day of Hackfort been? How many of you went to Treefort yesterday? Ooh, good crowd, cool. Man, it was busy yesterday. Actually, it's been busy here today. It's been a really, really fun Treefort so far. Well, my name is Sean Wakely. I'm the director of Hackfort. I really appreciate you guys coming out. I've been super, super excited about this talk. A good friend of mine, John Michael, who's sitting right there, introduced me to these two lovely women. This is Miriam and Leah. They are part of the Ada Lovelace Foundation. They came all the way here from Europe, and they've been having a fun trip, I hope so far, right? But yeah, I'm super excited about this. Thank you guys so much. It's so fun to collaborate the little bit we got to do online the past few months, and I'm excited. So I'm going to hand it over to you guys. We are going to have Q&A at the end. We'll be passing around a mic because this is getting recorded, so we want to make sure we capture those questions. Thank you, ladies.
Let's do this. All right. Thank you very much, Sean. And thank you for having us. This is Miriam. I'm Leah. And as Sean just mentioned, we are actually connected due to a wonderful woman that Joel in the talk right before us already dropped, Ada Lovelace. We have a company together named after Ada. And what we basically do, we are both researchers. Miriam is a professor at the University of St. Gallen in Switzerland. And I wrote my PhD on AI and what it does to society and to businesses, and what you can do with it. And what we do with our Ada company, Ada Learning, we basically work with various European governments and companies like Lufthansa, Telecom, Henkel, and a lot of large, at this point, international European companies that are trying to apply technology. So we train their employees. Every year we have around 500, 600 of their employees. We're trying to work with them on very applied technological problems. And we also put on 2 large conferences. And when we found ourselves at another conference in France, in a lovely rural France, we were sitting at dinner, and all of a sudden we realized we were sitting next to 2 lovely gentlemen, John Michael and Brett, and we realized that we share this passion for gathering people and for putting people together in a context where they can share their expertise and learn. So that's where the invitation came from. So thank you very much. We're so happy we made it all the way from Düsseldorf, Germany, here to Boise, Idaho.
Yes, that's wonderful to be here. And after having been stuck in the deep snow with very, very cold weather in Utah and in other places, we are almost feeling like a spring day today and really happy to be here. And there's another segue, apart from Ada Lovelace, connecting Joel's talk he gave before us to our talk. And that is basically that we are going to be talking about a technology that is really mind-blowing in many ways. And just to be warned in advance, if you have the feeling you don't understand anything about it, or not much about it, or maybe only a little bit about it, even after our talk, that might be our fault. That's totally okay. But it might also be due to the fact that even the experts in quantum computing don't understand quantum computing. And they're very, very frank about it. We will relate to that later. But the thing is, what quantum computing can do and why we have to deal with it, have to talk about it, is doing the things that Joel showed you, like using generative AI on a quantum computer that will blow our minds in terms of speed and capacity of computing. And that's why it's so interesting to deal with it. So that's our topic for today.
And we will first set the scene by giving you some of the foundations of quantum mechanics and what that means for quantum computing, why it's so different to traditional computing. Then we'll go into applications. What does that mean for businesses? How are we probably going to be using this? And then we'll end with using quantum as a metaphor and why we actually think that it might help you switch your perspective a little bit. And it's going to involve a lot of German men. Albert Einstein, Erwin Schrödinger. You will hear a lot of German gentlemen, and we will, as German women, do our very best to translate or to transfer what they have found out. But first of all, let's start with humans, with us in the room. We like to do this little exercise to make sure that we get a sense of who is actually in this room. So could you please stand up if you know more than 5 people in this room? Just to understand. Okay.
Not a lot of people. This is kind of interesting and also great, because then you have a lot to talk about later and get to know each other. So, second question, please stand up if you believe that a decision you have taken once has altered the path of your life.
Oh,
Oh, great.
nice. Oh, I would love
I
to
appreciate
go around.
that.
Would somebody like to share? Now I would love to hear, is it like meeting your partner, or is it, taking a job? Would you like to share?
It's like the butterfly effect, everything. Everything is constantly changing.
Oh, nice. Everything. So you're saying like every decision you've taken has taken you on a different path. I love that. Yes.
The butterfly
Over there.
effect. Yeah.
I was traveling in 2014 in Morocco, and I saw a post on Instagram asking for "This is Boise photographers," and I was like, "Oh, I don't think I qualify, but I should totally apply." And here I am, a professional working photographer on the photo team for Treefort.
Wow. From Morocco.
No, I was in Morocco at the time.
Oh, and you saw it on Instagram. Okay. Nice. Perfect. Okay. What about you, Joe Michael?
I met these two lovely German women in Portugal and then saw them again in France. And then they had us come to Berlin, and it led to this moment, and it's changed my life forever.
These two danced for the German chancellor, just so you understand. They did, in front of 500 people and Olaf Scholz. It was fantastic. All right, last one.
Last one. Please stand up if you sometimes feel two emotions at the same time. Because this is really quantum. What kind of emotions do you feel at the same time?
I think you could feel excited and stressed out at the same time. I think, I'm presenting at the end of the week, like at Hackfort, and I've been really stressed about it, but also really excited. So I think that, that's kind of two emotions I feel a lot.
We had the same because our flight was canceled back to Germany, and we are very excited to be able to stay longer, but actually somehow stressed by getting back in a way. Someone else, would you like to share?
Sure. I don't know. I think emotions can be more like a flavor, and so it's like however you want to subdivide it, you can subdivide it into whatever fundamental parts you feel. But I think it's more complicated than just a single sort of thing.
That's wonderfully put, like a flavor, and you cannot ask ChatGPT about it. You have to feel it. Yes.
All right, so we're very human in this room, which is amazing, but also we are connected to some of the principles in quantum computing. And Miriam, why don't you start us off with the foundations?
Yeah, let's just dive in. So whenever you look at this world and the way we look at this world, then we know that we kind of do it by differentiating. And how do we differentiate? We do it by either or. So you see this, you have a black square and you have a white square. That's very easy. It's either or. So if you take a second look, you see maybe even in that very simple way of discrimination, it's not that easy at all, because the description, white and black, is already taking the other color. So what is white and what is black now? And what does the text say? And what does the picture say, the color itself say? So sometimes we realize, even in the very basic distinction, either or, the world might be much more complex than we think. And that is true for this world, but we have learned it that way. And why did we learn it that way? Because of the way we compute. We are working with binary code, with a digital computer that is basically based on 0 and 1. Every information in this world is encoded in a series of 0 and 1. And that can be very complex because it can be a very long series, but it's always about either or. It's always about black and white. It's always about yes and no. And that is how the binary code and the digital computer works. And that, of course, has impacted our way of interpreting this world, of looking at this world in many ways. So here comes the future star of computing, the quantum computer. And the thing is that this computer works very differently from the digital computer we are all working with every day in our pocket, at home, on our laptops, whatever have we. The quantum computer uses qubits instead of bits. And that means a basic distinction. Because, as I said, the classical bit, the binary system, is either or 0, 1. The qubit, or the quantum system, is based on something we call superposition. And that means that the binary coding of information can be 0 and 1 at the same time, and everything in between. It's not either or, it's and. And that's a very, very incredible way of looking at this world, the world we are living in, because on the subatom level, this is how our world works. It's not either or. Everything is superpositioned, and it is taking different states at the same time. The subatom level of electrons, of photons, of whatever heavy, what makes everything that is existing in this world. We cannot see this in the world we are observing. Like, I don't look like everything at the same time. I'm basically on the macro level based on decisions we make. But basically, the quantum idea of this world, the quantum physics idea of this world is superposition. So let's get into a very tiny portion of math. You don't need to remember the numbers. Don't be afraid. It's just an example to emphasize a little bit what I was talking about. So if we have 3 bits, we basically have coded 3 basis units of information. And on the digital computer, it's basically 3 versions, because every bit can be either or. It's black or white, it's 0 or 1. In the quantum computer, as every qubit can take at least 2 states at the same time by superposition, it has a total different range. And you see that by just using 3 qubits, you can reach 8 states at the same time. 2 states for each qubits, a potential of 3 makes 8 different states at the time. If we use it a bit like a metaphor, it's not really correct, but it helps to understand what I'm talking about. It's basically that the digital computer would have 3 computers running at the same time by using 3 bits, and the quantum computer would have 8 computers running at the same time, because every qubit is basically in a superposition. So if you imagine a quantum computer with 300 qubits, by the way, IBM just came up with one that has 433 qubits. Still a quantum computer that can be used theoretically and for specific experimental reasons, but it cannot be used on a very daily broad range, because these systems are so intricate in many regards. But if you think of a quantum computer with 300 qubits, you could get to a number you see here that is basically larger than the number of particles that exist in the universe. Imagine that. 300 qubits, a number larger than particles exist in the universe. That is the power of quantum computing. And that tells you what happens when we use a quantum computer, for example, having quantum AI running on that computer. It's exponential. It's so much faster. And it's a so much broader scale of data that we can process that it is almost unimaginable for the human brain. But, of course, there comes a but, because the quantum computer, as I said, is a very intricate system. It has to be cooled down immensely. We have to really make sure that no environmental impact is somehow interfering with the qubits. Otherwise, the whole thing will break down, and you will not be able to use it. So there are many shades of gray in this quantum computer. And for example, some of you might remember that in the year 2019, Google made a great announcement. They said, basically, we at Google, we reached quantum supremacy, which means we managed to calculate something using a quantum computer, the Google Sycamore quantum computer, that a regular computer cannot calculate at all. And that was partly true because they managed to calculate a theoretical mathematical problem, and they used like 200 seconds to calculate that problem that no regular computer had ever been able to calculate. 200 seconds. Quantum computer. The best regular supercomputer, digital supercomputer, would have taken 10,000 years to calculate that problem. 200 seconds versus 10,000 years. That's the range we talk about when we talk about quantum computing. So you see that there is a huge potential, and we will come to some of the applications very soon. But we also have to acknowledge that not everything will be about quantum in the future. So I'm not saying every problem will be solved by using a quantum computer. We will need traditional supercomputers, and they're really good at many, many things because, for example, a Chinese team, quantum experts team, came up last year with the same mathematical problem that Google Sycamore computed and did the same computing on a regular supercomputer. They took like 15 hours. It's still much longer than 200 seconds, but it worked. And so there goes the supremacy. That's always a little bit difficult to handle those terms. They might come back at you like a boomerang at one point. But what I'm saying is that we will have a collaboration between regular computers and quantum computers in the future, and that will be the most interesting thing. And these are so many shades of gray we have to keep in mind. Shades of gray that the former CEO, Ginny Rometty, the former IBM CEO, Ginny Rometty, once at the World Economic Forum in the session we both attended, mentioned, and she said something very funny. She said, quantum computing is so great, but there are many, many shades of gray in quantum computing, and actually there are many more than 50, just for those of you who have read the book. So we have the superposition as one thing, and maybe to give you a little bit more of context for that, the ability to be in multiple states at the same time. There's a wonderful example showing how unfathomable that is for the human mind, and that example comes from an Austrian researcher and expert, Erwin Schrödinger, because he came up in 1935, with the idea to disprove quantum computing. He did not like quantum computing because that went totally astray from everything we thought we knew about physics, Newton, all these kinds of things. And there was another guy from Germany, as Leah said, Albert Einstein. He didn't like quantum computing either. He said it was spooky. Really spooky. And then Schrödinger thought, well, we will prove that this is bullshit, basically. So he wrote a letter to Einstein, and he wrote, you know what, Albert? Think of the idea that quantum mechanics is assuming the world works and take it on a macro level. So this would be this experiment, and this is how Schrödinger came up with it. He said, we take a wooden box and we put a cat, which is alive, into the box. And with the cat comes a whole intricate system with a nuclear atom that decays in a certain time. We don't know how quick or how slow it does that, how quickly or how slowly it does that. And if the atom decays, it sets free radioactivity and a mechanism that will make the cat die. It's kind of cruel, isn't it? So it would be forbidden today, probably, but 1935, it could be imaginable. And so Schrödinger came up with this idea. He closed the box and he said, so if quantum mechanics is right, at this very moment when the box is closed, we have no idea whether the cat is alive or it is dead. And if quantum mechanics were true, the cat would be both at the same time. So this is real bullshit.
May I just add, in Schrödinger's experiment, that box should be not transparent because otherwise you would see the cat. But this is, just to allude to your talk, Ken and Joel, this is what generative AI gave me. This is Midjourney. When I asked it to give me Schrödinger's cat, it literally gave me a transparent box. I thought it was hilarious because the whole thing doesn't work. But
also
enjoy.
With some text on it, some gibberish on it, like always. Yeah, so that is the experiment. And you understand what they were up to. They were saying, it cannot be true what quantum mechanics is telling us because in the real world, it wouldn't work. And the thing is, that is right. It wouldn't work in the real world. We know whether we are alive or whether we are dead. And that's great that we know, actually. But in the subatom world of quantum mechanics, this is actually how our world works. It's all at the same time, and the cat would be dead or alive in the same time. And only if we as an observer start to observe, then the situation falls apart and the qubit, for example, takes a 0 or a 1, and then you can decide. But whenever this is not observed or measured, it's both at the same time. So this is basically how this funny experiment worked, and it's world famous, a crazy idea by Erwin Schrödinger, but it's very helpful to understand how this superposition is meant to work and why it is so really hard to understand for the human mind. So coming up with a second idea about quantum computing. Superposition is the first one. Entanglement is the second one. And that's also as interesting because it means that qubits in a quantum computer are always correlated, quantum correlated. That means they are entangled and they interact with each other in many regards. And even if they're far apart, that is still true. So that means if we had a qubit like on a photon here in this room, and a qubit on a photon attached to a photon like where we come from in Germany, and they're entangled, which they can be, if one photon changes, this one here in this room, the photon in Germany changes equally. That's the principle of entanglement. And that's another challenge to our imagination as humans. How can that be? Nature is fascinating. It's almost mystical in a way that gives us the idea that something has evolved in our world that is really gorgeous.
Okay, so those are the two basic principles, right? Superposition and entanglement. And because of those two principles, quantum computers are able, as Miriam mentioned earlier, to first of all compute very, very fast and a lot more data than traditional computers can. And so with these two principles and those consequences in mind, let's have a look at some of the possible quantum applications. We've talked to a lot of companies that are currently in basically the R&D phase, trying to understand what could this mean for us? What could be a quantum problem where this kind of physical knowledge, the knowledge of quantum mechanics, could actually help us do things more efficiently and effectively? Are there any cryptographers in the room? Or anyone that has to do with cybersecurity in the larger
over
sense?
there.
Oh, I'm sorry. Did you? Oh, the photographer is an That's amazing. That's wonderful. So number one, and probably you have heard quantum computing in relation to cryptography in the news, because this is really something that the field is trying to grapple with. So the current way of doing cryptography, or one common current way of encrypting our information online, is RSA encryption. And I'm sure you could explain that in even more detail, but basically, to break it down, RSA encryption works in the way that you have two keys, a public key and a private key. The public key, I see you nodding, you probably also know what I'm talking about. So the public key encrypts your information, the private key then decrypts it and helps to uncover it. And it does so by having to determine two large prime numbers. And a traditional computer would take years to be able to break that, to understand, especially if it just has one part of the key, to understand what numbers have been involved. With quantum computing, it would basically be possible to decrypt, to uncover everything that we have currently encrypted on the internet in a matter of hours, if not minutes. It will go so fast that if this happens, if quantum computing at this level comes about, all of the encryption on the internet would basically be broken within a matter of moments. So right now, the field is really trying to figure out and to prepare. They're trying to prepare for that moment and trying to understand what to do now with all of the encrypted information on the internet, for that moment when basically one technology will break it all. With quantum computing and its version of cryptography, so with quantum key distribution, it would work very differently. It would work in the way that Miriam just described, with entanglement. So if you have two entangled quantum objects, imagine two pieces of information that are entangled. If somebody tries to intercept that information and thereby changes one part of that qubit entanglement, the other one would instantly be affected as well. And we would instantly know that somebody has basically meddled with this entanglement situation, that your unit has been messed with. And that allows basically, first of all, the encryption to be much, much safer, But again, it also means that if we're at this point, we will have already broken all the currently encrypted information on the internet. So there are currently coding challenges by, I think NIST has one very large one, the National Institute for Standards here in the US, trying to basically get people to come up with ideas to make sure that we can somehow very rapidly re-encrypt in a much safer way everything that's out there on the internet right now. So that is one field. Cryptography, if quantum computing comes at scale, will definitely be impacted in a major way. Now let's think about what happens when quantum computing gets entangled, gets combined with machine learning. So imagine everything that we just heard about and all the other applications of AI more generally and machine learning specifically. Imagine if somebody put like a firecracker in it and just went, this goes so much faster. So remember Miriam's numbers, 200 seconds versus 10,000 years? Imagine that speed and capacity in an AI system. So what we are expecting in the next few years, I'll give you a timeline in a moment, but in the next few years, it is not the case that we're looking at quantum computers, coming around basically taking on all the tasks. We're not there yet at all. The first step will very likely be a hybrid version. So meaning a quantum computing system will be used for part of the calculation, while the rest will be running on a traditional machine learning system. So what does that mean? What can we use it for? So for example, one of the areas that we just actually heard an expert talk on at South by Southwest, she is deeply involved in quantum computing for weather prediction. We all know that climate change is happening to a larger degree than is naturally normal. So to be able to predict what is going to happen to the climate, which is, as we all know, chaos theory, pure chaos, right? The climate is notoriously hard to determine because it has so many parameters, so much detail going in there. So quantum computing could majorly improve our accuracy and our sort of the duration that we could look into the future and that we could forecast to be able to actually monitor the climate. And again, in combination with machine learning, we could also improve our pattern recognition and understand more extreme weather events that are happening. Again, give it up for generative AI on the right. This is what it thinks the climate will look like. Just love it. Second, and this is really an area that I'm very excited about, even when it comes to just AI, forget quantum, but add on quantum and it will be insane. So who here heard of DeepMind's AlphaFold 3 years ago? So that was a breakthrough. Google's DeepMind research arm basically came up with AlphaFold, which it was happening during a competition that they held to be able to use machine learning to predict the protein folding structures that you, again, beautifully done by generative AI, see here on the right, but they actually do kind of look like that. At least the Google visualizations also look like it. Basically, it means what used to take us years to predict, which is the exact foldings of a protein of different molecules, can now be done within hours. Why is that exciting? It means that we can discover and develop medicine in a much, much faster way. Drug discovery and basically understanding certain biological structures will just be advanced by, not tenfold is probably an understatement. It was a huge breakthrough. The biological community really celebrated that when DeepMind came out with AlphaFold 2020. Now imagine that we add on the capacity and speed of quantum computing to something like drug discovery. Now, while we're on the topic of simulating natural structures, think of traffic systems, think of epidemic predictions, or even pandemic predictions, general population trends. Think of anything that involves a huge amount of data. AI to the max, right? We're already able to collect and analyze so much data, but now think of so much more that is possibly analyzed. Optimization, think of large models, for example, stock markets and everything that basically, as I just said, involves a whole lot of data points that are very rapidly moving and that are difficult otherwise to grasp. And
think of the financial
analyze.
markets and taking the
yes.
human out of the equation in running institutions like Silicon Valley Bank, where the quantum AI might have done a much better job actually than what happened there.
Now let's look at one example because we had a deep look into that when we were invited to speak at Volkswagen's Global Top Management Conference last September. in Portugal. Again, it was also in Lisbon. And they were really trying to grapple, they are trying to grapple with the question of what this could do to their industry. So McKinsey actually predicts that 1/10 of all the use cases of quantum computing will actually at least impact the automotive industry, because it has to do so much with different parts that are moving and data points coming in. A lot of money to be made there as well. But let's look into this. What does it actually mean? So quantum computing could, for example, be used for optimized traffic flow, right? Again, this is something, as you know, it involves a lot of human behavior. It involves a lot of data points. Imagine being able to, in real time, predict and maybe even better guide, by traffic lights, etc., guide traffic flow. Again, here the idea of material discovery is very important. Volkswagen is actually also using it again in the R&D phase, but they're using quantum computing to come up with the best material combination for electric batteries for their EVs, which is also kind of cool. And of course, also in the realm of autonomous driving. Don't know if that'll ever come. We've had some conversations with certain CEOs that are very unsure about that. But anyway, they are trying, and quantum computing could, of course, also aid that. And as I mentioned, Volkswagen actually did 4 years ago in 2019, they actually had their first sort of launch together with D-Wave Systems of an actual pilot project to optimize traffic flow in the city, which is pretty cool. So they're really grappling with this question. And again, 4 years ago, so you can imagine where they're at now. This is really coming in the next few years. So, well, that's so cute. Look at those flags coming first. So also, governments have really begun to understood that this is a realm that they should really invest in now. We, in our last interview with Angela Merkel, you, Miriam, I remember, asked her also about quantum computing, because Germany is kind of known for not being the first in technological things. We like to wait a lot. Angela Merkel liked to wait a lot with technological initiatives, but with quantum computing, she kind of saw this as, a real foundational technology that could be a breakthrough, like AI is now, could be a breakthrough in 10 years to come. So what we're seeing is huge amounts of government funding. China, far, far ahead. The European Union, granted we are multiple countries, but the European Union also ahead of the United States. But you see also certain, individual investment initiatives. France, 2.6 billion. This is all US dollars. Germany, the US, Canada. So there's really a whole lot of money being poured into this right now. Again, because people are expecting this to kind of go through the roof in about 10 years, like AI is currently having a moment. And as we all know, AI is not new. We've been talking about it since 1956. In the last 20 years, it's just sort of gone up because of computing power and lots of money being poured in after lots of AI winter in terms of funding. So let's look at the actual timeline. In the next 5 years, I would say most of the use cases will be done by a combination of quantum computing and machine learning. As I said, it's a sort of hybrid setup, if anything. And I say if anything because Miriam mentioned this at the beginning. At the moment, there are quantum computers mostly in really large research institutions or companies like IBM, like Google, and there are some cloud providers that offer people to actually use their quantum computing capabilities for their own applications, like StrangeWorks. I don't know if you guys know Worley. He's a friend of ours, and we're working with him actually on a research project on quantum computing. So StrangeWorks offers as a provider for you to use their capabilities. But at the beginning, it will be simple optimization problems and mostly as a hybrid setup. And then in 5 to 10 years, it will basically be more complex, and we will move into the possibilities of real-time simulations and more complex problems. And then, at least this is what the experts are saying right now, from 2030 onwards, although at this point that's only 7 years ahead, but 2030 onwards, we're looking at potentially having quantum computing at scale. I think at scale will still not mean that we will all be accessing it in some sort of easy accessible interface way. I think it actually will take a little longer than that for that to happen. But at scale, meaning that many, many businesses will actually have access to it, which at the moment is not the case just yet. If you're interested from an academic standpoint, we did write a paper on it just for all the sort of foundations. And this also includes a lot of the market analysis and the sort of business applications, if you're interested in it. This also includes some business insights from certain European companies that we included. But that is it for the applications. I'll just leave this up. You got it. Somebody bashed the QR code earlier today.
Yes, this morning.
I
We
don't
love the
understand. I
QR
love
code.
the QR code.
So
Somebody
we have
up
it,
here
of
was like,
course,
who
in
hates the
our-
QR code? I was like, no, look at the QR code.
Maybe one more remark regarding the timeline that Leia just pointed out. There's one important question hidden behind that we should keep in mind, because as you said, quantum is so complicated. It's very expensive to run a quantum computer, and that's the reason why Google, IBM, Amazon are working on it. And it will be a technology that will probably not be on our desk at home. You will not work with a quantum computer at home in the next couple of years, maybe never, I don't know. Which means the potential to, the opportunity to access the power of quantum computing will come via the cloud. And the question that is related to that is, will we be able, different from some other technological developments in the past and in the at present, will we be able to open it up to everyone to make it an inclusive technology? That's a really important question, because otherwise we will have a multiplication of the situation of having a couple of companies offering everything, making tons of money, which is okay. I don't care, but leaving many people out from taking advantage of this technology, and that will be really sad, because it will also impact the power of each and every country and region to really participate in that and to use the technology to really develop in a way others can do then.
So now we want to move in our last third into the idea of quantum as a metaphor, because we heard those two big principles, right? Superposition, meaning basically being able to hold multiple states, being able to be ambivalent about something until it is being measured, as they would say in quantum physics. So that is superposition. And then entanglement, the idea that everything is connected and something that you do or something that happens to you does affect your entangled little qubit on the other side.
Yeah, we thought before you get swallowed up by the music festival and all your evening activities, we want you to get active first on your own for like 2 or 3 minutes, and then talk to your neighbor about this question. How might the principles of superposition and entanglement that we described impact your mindset? What changes might come out of the idea of quantum as we described it, for how we look at this world, how we perceive this world? Take a couple of minutes and then talk to your neighbor briefly about it, and then we will hear some of the
voices.
Should we
say 2 minutes brainstorming by yourself, and then we'll have a quick exchange with neighbors, and we would love to hear some of it. We've done this with many different groups, and sometimes it's fascinating. If you think about like your professional mindset or your personal circumstance. So how could these two ideas, superposition and entanglement, impact your mindset? 2 minutes. Wish we did have like gaming music or something.
So that was wonderful to see that you really engaged in talking to each other. And whatever you have talked about, at least you got to know one more person in this room than you knew when you came in. And maybe you want to get a little bit entangled in the course of this evening and night. No one knows. So, but we wanted to understand what you think about the principles of quantum computing and what they do or they might be able to do to our worldview. Who would like to share some ideas? Anyone? Come on. Yes, I come to you. Oh, you have a microphone. Great.
So I was thinking of globalization and how technology has really allowed for globalization. Previously, the amount of time that it took to communicate between Europe and the United States, it was slow. It made for communication to take some time. But technology, we can instantly communicate with our current level of technology. Still with our current level of technology, if we have a lunar colony somewhere out in the universe, there is still a lag of time in which communication takes place. And so I think with entanglement, at least, you'd be able to at least apply globalization on a universal scale or perhaps even larger.
Oh, that's a wonderful idea. Thank you for sharing. Great idea. Yeah. Who else would like to add and share?
So first off, can you hear me?
Yeah.
Okay, perfect. So first off, you guys are brilliant. So thank you so much. I feel like
Thank
a caveman here trying to understand this stuff, but you guys are brilliant. So I just have a question. Hopefully I can pick your brain a little bit. As far as quantum entanglement, how does that reconcile with the theory of non-local causality as it relates to what we know about physics and whatnot? Does that make an effect, or is it just kind of an asterisk on the side?
I think as far as I know, at least there is no direct combination, but actually, when I think about it, it goes in the same direction, basically, explaining that there might be connections and interrelations of things in this world existing in this world that we cannot explain by our regular thinking. And I think that's basically the overall perspective we wanted to get at by this little exercise. And I would have to really dive deep into whether there is some connection, but I don't know about it. I don't think so.
Awesome. Thank you.
So you made me think, and it tickled my brain. And so I was thinking, if I exist in two places at once, how does that affect free will? Like, is one of me affecting the other? Is that the person making the decision, or am I making the decisions? Who's in charge here?
I love that you went there. First of all, who has seen Everything Everywhere All at Once? Oh, thank you.
Yes.
I mean, that movie, all the worlds, because there's a lot of quantum in there, by the way. We did a whole podcast just on like the idea of quantum physics and Everything Everywhere All at Once. Free will is such a long discussion. We did a whole Ada Lovelace festival just on quantum computing, and Miriam did an interview with the president of Armenia, I think it was, who has such distinctive ideas about free will and like multiple versions of you and how they affect each other. So basically,
he is a quantum physicist.
He is.
By the way.
I should have said that because otherwise
a trained
it would be
quantum
weird.
physicist.
Forgot a detail. Yeah. Very important. He does actually have that background, but it's a great question. So what I love, since you asked, does one decision of one me affect the other one? I recently listened to Sean Carroll, also a quantum physicist, explain entanglement in this wonderful way, where he actually said the qubits do decide on something. And if one entangled qubit decides on something, let's say 0, the other one instantly is affected and has to be 1. So the short version, or the physics answer would be, yes, actually, that one decision with you being entangled would affect the other decision. I loved how he said, think of 2 gloves. And if you don't know if it's the right one or the left one, and you look at one and they're entangled, and it is the left one, the other one has to decide to become the right one. Just love it. He uses those like decides and has to and become. Because if they're entangled, you do have to basically be the polar opposite. So yes, I think in that world, and if there are multiple versions of you, one decision would affect the other one. which makes me think of Everything Everywhere All at Once in a whole new light, because she makes all these amazing decisions. And I want to have that thing to just be transported elsewhere.
Directly to, yeah.
Hi. We were talking about, say you have a decision in your life. Do you choose A, B, C, or D? If there is a multiverse and you choose A, then all the other multiverses will choose B, C, and D. And therefore, going to your mindset, whatever decision you make is the correct, right, the pathway you're supposed to take, because it will lead you to the next decision, the next outcome. And all the other decisions will be made by other yous. And so you don't have to worry about making the wrong decision ever. Whatever you choose is the way you're supposed to experience the world or your existence.
And isn't that a relief in your life? Isn't that wonderful?
That's
Yes,
really cool.
that's brilliant,
I mean,
yep.
and that's also part of the official theoretical discourse about quantum physics. That there is the theory. Hugh Everett has come up with it in Princeton, like 50 decades ago, of the multiverse. And you actually, they actually say, the theory actually says that whenever you make a decision, you split the universe and you exist with that decision in that very universe, while another you, many other yous with other decisions exist in other universes. And there are very, very reputed people believing that this is true. And even if we don't want to go into the detail, if we use it as an like a little click in our head to think about what that means, that also means there is no determinism. There's no determinism in life. And that might help in many ways to understand that we have much more options than we often think. By the way, also good when flights are canceled.
I was just thinking that we made the right decision to book that flight that has now been canceled. There's a reason why we are supposed to stay here longer.
So maybe one more idea that we would like to hand over to you in the last 2 or 3 minutes is that, of course, this idea of entanglement and of superposition also allows us as humans to look very differently onto this world we're living in and to interpret it very differently, like in the way the multiverse offers us. That's one part of it, but also in a way that things not only can be ambiguous, they often are. They basically are, when we look at the very, very subatom level of how our world is made and how it exists. And this means the whole idea of this world of being like partisan. Everything is about being yes or no, being black or white, being against or for something, is basically a big bullshit we have come up with as humans. But that is not what nature reflects to us, and that should give us some thinking. When we went to the World Economic Forum, we also listened to a wonderful talk by Tom Friedman, the Economic Nobel Prize winner and columnist of the New York Times, and he said, if we want to understand quantum, we basically shouldn't think of throwing a coin where you always have heads or a tail. It's either or. But you basically take the coin and you spin it on a table, and it keeps on spinning, and you look at the coin from above and you always see both sides, heads and tails. And that is what quantum means. There are always many sides, and we can all see them if we are able and willing to look at them. And the interpretation that has so impacted our lives in different countries, be it in the US, be it in Germany, be it in Europe, be it in Latin America, that everything is about binary coding, is about binary understanding and making a distinction between you and me, good and bad, yes and no. This is maybe the wrong way, and we should try to reconsider, to use the hints that quantum mechanics give us to reinterpret our world. And whenever you have looked at this or a similar picture, that's the very easy way to understand what I mean, and that we are able to do this as humans. Because if you look at that, you see different things. Who sees a duck?
Who sees a rabbit? Oh, nice.
Yeah.
Wonderful.
And if you know that it's a duck and a rabbit, and you can make your mind see both things. You can switch back and forth all the time, and it's always that a part of the group, mostly the larger part, sees the duck because the head of the duck, the shape of the head is the more normal shape, because the rabbit kind of looks up very strangely. But a part of the group always sees the rabbit. That's what it is. We see different things in this world, and that's basically what quantum, now it's, yeah, that's easier. What quantum tells us, and that's a great opportunity to rediscover our world. And if you now, as I mentioned at the beginning, have the feeling, well, I have some things to think about, but maybe I haven't understood everything, that's totally okay. Because even Richard Feynman, one of the, gods of quantum computing and quantum physics, says, I think I can safely say that nobody understands quantum mechanics, especially, by the way, and that's also what Feynman says, those who say they understand quantum mechanics really don't. And coming back to the segue that Joel gave us so nicely at the end of his talk, we love Ada Lovelace because she was a very, very fine and foresighted woman, very clever at the beginning of the 19th century. And she said, the computer will not only be able to compute, to calculate, it will be able to compose poetry, and it will be able to make music. So basically, she saw AI, generative AI, coming at the beginning of the 19th century. That's some kind of intellectual capacity, I would say. And also, we love her because she's so modest. She was so modest about what we understand, what we can understand as humans, and that this doesn't necessarily mean to be a problem. She says, understand well as I may, my comprehension can only be an infinitesimal fraction of all I want to understand. So if we now today gave you an infinitesimal fraction of understanding quantum computing, or maybe getting interested in quantum computing, that would be quite a lot for us. Thank you so much.
Thank you very much.
Oh my God, thank you guys so much. That was so awesome. If you guys have any other questions, I'm sure they'll be hanging around for a little bit. Thank you guys all so much for coming out for the first day of Hackfort. Please come back tomorrow. We have an amazing lineup. Robin Fink from Nine Inch Nails is here. He's talking about his new video game. One of my personal heroes, Scotty Allen from Strange Parts, who's a maker and just an incredible video maker and storyteller, is going to be here before Robin as well. And then I've got Ryan Douglas, who's in the back of the room on Saturday. We have such a cool lineup. Please come out, have fun, say hi, be safe. Oh, see, John Michael is so good at this, and I feel like I have two amazing new friends because of John Michael. Thank you, ladies, so much for making the trek out here. Let's give him another round of applause. All right. I will see you guys out. Be safe, be fun, be kind.